today we will read the algebraic structures. Mainly in this study of algebraic structures, we will read how we can define the algebraic systems, their properties, and then we will try to identify that between two algebraic systems what are the properties shared, and so that they are structurally they can be identical, or what relations are there in respect to their algebraic structures. We will read So, first we define the what do we mean by algebraic systems. Normally algebraic systems, there the examples are that we know that these are group, ring, field, and the more simplest form semi group, monoid, like that. So, first we try to define that algebraic systems. So, it is consists of a set. So, algebraic system consists of a set, or rather we call non-empty set, and some operations. On the set, and they hold some properties, and based on these properties we will try to identify the different systems. And so, main systems and then their properties, we will try to identify the structures they hold. So, here the main important thing is the operations that on the set that we define, and the properties also. So, first we define that what are these operations. Okay. So, these operations, normally this can be some functions, some transformation, or sometimes we call some function, means sometimes we call it is a mapping. So, these operations that can be a unary operation, like unary operations like or subtraction, unary minus, we call the unary operation as unary minus, then our binary operations, where the operation that it operates on the two operands, like plus or simple multiplication, division, all this. Now, in general I can tell in general that it is some n-ary operation, n-ary operation. So, this n-ary operation I can define that in general I can n-ary operation we can define that if we consider a set non-empty set A, then an n-ary operation associates an element of this set to an n-tuple where each member is in set A. So, normally we call an to A. So, this is in general the n-ary operation. Now, this can be a binary operation, this is A cross A to A, and our addition is a binary operation like that. So, now we can formally we can define our algebraic systems. So, now if we define our algebraic systems, since we know the set, we know now the operations on the set S. So, we define algebraic system. Okay. So, an algebraic system or sometimes we call it simply an algebra is a system that contains a non-empty set S say A and one or more operations. Just now we have defined the operations on the set A. Now, if the operations are denoted as F1, F2, say this, then the algebraic system is we define as A, F1, F2 in this way. Now, I can give that, otherwise it can be. Now, in addition, if we add some relations with this algebraic system. So, in addition, if we consider some relations say R1, R2 defined on the set A, that is I can denote A, F1, F2, all these operations, and R1, R2 with all these relations, then these form a algebraic structure. Then this system form a algebraic structure. So, in summary, I can tell that algebraic system is a set, non-empty set with some operations on it. And if now we define some relations on this set, then this set, non-empty set A, along with the functions and the relations, we can tell that these are my algebraic structure. Now, first we see some general properties. So, we read some general properties, because based on these properties, first we will try to identify these properties and we will be defining the different algebraic systems or algebra. So, some general properties of now, first we see that the operations that just now we have defined the algebraic systems, the set, non-empty set A and the different functions or operations F1, F2, etc. Now, these operations that we call, these are closed operations. That means, what do we mean by closed operations? That, say, if I consider that, say, my addition, the set is, okay, the set is integers, say integer, normally we denote as Z, and the operation is simple addition. Operation is our simple addition. Now, if I take element A and B belongs to A, then A plus B, this is now here it is Z. So, that is here A B belongs to Z, integer. Then A plus B also belongs to Z, because Z is set of integer. So, on the operation under the operation plus, that the element we get, the A plus B, that also belongs to Z. So, this is, it calls the property of closure, or this operation is closed, it is the closed operation. Now, we see another say example, we okay. Say I take another example of the set we take, the set is a set of odd integers. Set A is odd integers. And the operation is say addition. Now the addition or this, it is not closed. It is not a closed operation, or closure property does not hold. You can write the closure property does not hold under this addition for this set of odd integers, since here if I consider that E1, okay, two odd integers, I consider that O1 and O2 are two odd integers, then O1 plus O2 always this will be equal to the even. This is some even integer, and so we have considered that O1 O2 belongs to A is set of odd integers, A is set of odd integers, then O1 plus O2, O1 plus O2 does not belongs to A, since it is even. So, it is not closed. So it is not closed. So, now we start that we write all the general properties of algebraic system. So, since now we know the closed operation, or we can even write the first property is the closure property. So, the properties so I give that we give some name that this is A1, this is the closure, and closure under say addition. That means here we consider that two operations. When this system we consider two operations plus and dot. With these two operations we try to identify the properties. So, and I can write closure with plus and dot. Now, I give the property of A2. A2 I consider the property of associative property. With respect to addition. Now, if I consider a say element A, B, C, so we consider set A and where A, B, C are the belongs to A. Now, as just now we have defined the closure means that I can write that some A B belongs to A, then A plus B belongs to A dot B belongs to A. Now, associative property, I can write that A plus B plus C equal to A plus B plus C. Now, I write property A3 which is commutative. With respect to addition, that means A B belongs to A, then A plus B equal to B plus A. I give property A4 is my identity exist, some identity element say here 0 is the identity element with addition. So, identity is that I get A plus 0 normally if E is the identity element. So, A plus E is E plus A equal to A only. So, in respect to addition we know that A plus 0 is 0 plus A is A. So, 0 is the identity element. So, here E equal to 0. Now, I get some inverse element. So, if there exists an element in the set A such that if AB belongs to A such that A plus B equal to the identity element. So, here it is 0 equal to B plus A. So, then B is the inverse of A. So, additive inverse of A. So, say A minus A is the additive inverse of A. So, additive inverse exists here. Now, if I consider the property with respect to my multiplication, say dot. So, again this I can consider the associative property, with respect to dot. So, I can write similarly that then multiplication that A dot B dot C is A dot B dot C. Then A7 is the property is called the commutative with respect to multiplication, and we can write A dot B equal to B dot A. Now, we write the property A8. So, the identity element with respect to dot, and we know that one is the identity element, since A dot 1 is 1 dot A equal to A. So, 1 is the identity element. Now, I can write 9, that is the my distributive properties. Now, we have two operations. So, I can write two operations plus and dot. So, distributive properties with respect to addition and multiplication. So, I can write A dot B plus C is A dot B plus A dot C, or B plus C dot A, I can write B dot A plus C dot A. So, here I can write that multiplication dot is distributive over addition. Now, I can write two other properties, that this is called the cancellation property, that I can write that if A dot B equal to A dot C implies B equal to C if A not equal to 0. If A not equal to 0. Now, another is idempotent property. That is A dot A equal to A and A plus A equal to A. So, normally these are the properties, and two operations A plus and dot we define, then these are the properties we will study on the set A. Now, we take some example that how actually these properties are hold, and identifying those properties we can define some algebraic systems. So, one simple example is, say, the algebraic system say set of integers, and the operations are simple addition and multiplication. Okay. Now, we can see that this algebraic system satisfies all the properties that A1 to A10, all the properties A1 to A10, but not the idempotent property. Now, we consider another one, that another example we consider, which is the we consider the set of 2 by 2 matrices. Okay. We denote say 2 by 2 matrix on integers values m to z are all 2 by 2 integer matrix, and the operations are simple addition and multiplication. That means my system is m to z plus and dot. Now, you see that addition, under addition all the properties, that means it is closure, associative, commutative, identity elements is also there, that so it will be up to A5. We see that m to z, if I consider plus, that means this algebraic system satisfies all the properties that up to the A9, the distributive element, because I am taking all the properties A1 to A9. Here the with respect to addition, the identity element is element is 0 0, because if I add, if I take say 2 4 3 1 plus 0 0 0 0, I will be getting element wise addition. So, this is 2 4 3 1. Then with respect to multiplication, the identity element is 1 0 0 1. Since if I multiply 2 4 3 1 to 1 0 0 1, simple matrix multiplication, we will be getting 2 4 3 1. Now, the inverse also exists. The inverse element with respect to addition, this is, say if it is say 2 4 5 3, the inverse is -2 -4 -5 -3, because this is the my additive inverse. Now, in this way we can see that it is commutative, it is under addition and multiplication, but only the cancellation does not hold. Cancellation means our property A10. A10, why? That property A10, that is cancellation does not hold. Since if say if A is 2 by 2 matrix, say it is 0 0 0 2, and I consider B is something called 1 2 5 6, and my C is 7 8 5 6. Now, see that if I multiply AB, then this AB is 0 0 0 2 is 1 2 5 6, and this equal to, this is 0, then this is also 0, this is 0 2, that means 0 into 1, 2 into 5, 10, 2 then this is 10 and 12. Similarly, if I get A dot C, then it is 0 0 0 2 dot 7 8 5 6, then I also get 0 0 and 10 and 12. So, I get A dot B equal to A dot C, but we see that then also B not equal to C, even my A is not equal to 0, A not equal to 0. So, cancellation property, this cancellation property does not hold here, and idempotent does not hold. So, if I take another example, say if we consider the power set of S, we know the power set of S, we denote PS, and the two operations we said, the union and intersection, okay, the sum and product. So, the union and the intersection, union and intersection. Then our phi, the null set or empty set is the additive identity, and the set itself S is the set itself is the multiplicative identity. However, here there is no additive inverse exist. That means, this additive inverse is the inverse element, that A5. So, there is no A5. So, in this way we can actually, so this is that A5 is not there. So, in this way we can identify the different algebraic systems and what are the properties they hold. So, in the next lecture we will try to identify that our many common and popular algebraic systems, and we will see that what are the general properties they hold. Actually, the properties they are satisfying, based on this, that actually the algebraic systems are defined, and then we will study their properties also.